Alrighty. So for those of you that I haven't met, I'm Brian Lin. I am the OSG software team manager, and today I'm going to be talking about running jobs out on the Open Science Grid. So far this week, you guys have learned about high throughput computing and HTCondor in a local scale. Perhaps maybe not local to you, but all of the computing resources are based in the Madison area here. Let's say you have some sort of deadline where you need to get a lot of computing done in, say, the next week or so for a conference or a paper of some sort. And you log into your local UW-Madison Submit cluster, get on to Learn. And to your horror, you see that all of the computing resources are currently being used. When you speak to your local facilitators, they say, yeah, there's some big projects going on right now, and we don't see this letting up, at least in the week time frame. So how do you get more computing resources? If you know the local systems administrator, perhaps you can convince them to give you some higher priorities so that you can sneak some jobs in there. My experience, a lot of them are pliable with beer. But that is a little crazy, so we'll have to keep that solution in our back pocket. What else can we do? First off, the most obvious thing is to just buy the hardware yourself. And this is really great for specific hardware needs, say GPUs, or privacy requirements. If you're working with HIPAA data, you shouldn't be using any sort of high throughput computing that's shared with other groups. The only problem with this is that it costs a bunch of money. And not just the initial cost, there's the maintenance cost, there's paying people to manage these resources, there's the power and cooling costs, the cost for housing the physical servers, and then you have to replace these servers every couple of years as they die or as your research computing needs become bigger. And in the case where you have a deadline, that's probably going to be your peak usage throughout the year. I assume that many of you will have computing workflows that are very bursty, that you'll submit a bunch of jobs, get your results, do your actual useful research, and then you won't use the computing maybe for a couple of weeks or maybe even months. But during that entire time, you're going to have to pay for the management, maintenance, cooling, space, et cetera, et cetera. So you're going to have to plan for your peak usages and then pay for all usage. And then finally, this doesn't really work within our time frame because delivery and installation of the hardware takes some time. A second option is to use the cloud. And there are a lot of cloud providers out there right now. Amazon Web Services, Google Compute Engine, Microsoft Azure. There are plenty others. One nice thing about this is that you don't have to wait for the hardware delivery and installation. There's very quick start. Still costs money though, and you still need somebody to actually manage the resources. This is a little bit easier these days with the Condor Annex tool. It can talk to a bunch of these cloud providers and then start up Condor workloads for you. Additionally, you have to worry about whether or not this fits into your institutional grant policies. Have you budgeted for this type of expenditure for computing resources? Or is it possible that if you have a large enough computing need that you may have to actually get bids from various cloud providers? Another option in the cloud is to use what are called managed clouds. There are companies like Cycle Computing and Globus Genomics. And basically what they do for you is they manage the cloud resources for you. So you tell them that you need this number of cores with this much RAM, and they'll set that up for you and have it join the Condor pool, and then you can submit your research. However, of course, this still costs money. But researchers in industry have used this to great success, and I've linked a bunch of the Condor Week talks from previous years where folks have spoken about these solutions. So a lot of these, or the options so far, require spending money, which may make sense if you are managing a lab and a budget, which many of you may do someday. And you may tailor your resources to your particular research needs, like I said, in terms of maybe GPUs or HIPAA data, for example. But I imagine that many of you are also pretty early career researchers, and so you don't necessarily have that money to spend. So there is a third option that we call distributed high throughput computing. And when I say distributed, this is geographically distributed. So a lot of the servers here in Madison aren't necessarily in the same server room or building, but we still call that just regular high throughput computing. Distributed high throughput computing will look a little bit like this. So like UW-Madison has a Condor pool. The University of Nebraska-Lincoln and the University of Chicago all have clusters where their users can support or submit jobs for their research, and we call this distributed high throughput computing. So you can imagine if the UW-Madison cluster is full, the Nebraska and Chicago clusters may not be. And so if you can somehow get access, then you could submit your jobs to either of those clusters. And we'll call this manually dividing the jobs. So what would this strategy actually look like? First, you would need to obtain the login access to those clusters, and then you would query each cluster to see how many idle resources are available at each of them. Then from there, you would divide your jobs and submit them to each of the clusters based on the different resource availabilities. So that's great. In this case, maybe you would send most of your jobs to the University of Chicago and then some of them to the University of Nebraska because there aren't as many idle resources at Nebraska. But what happens when all those clusters are full? Maybe everybody's going to the same conference and they're all doing their computing. You can kind of see how only having access to a few resources kind of just kicks the problem down, kicks the can down the line. So there are some shortcomings here. The fewer logins to other clusters means that you have fewer potential resources. But on the other hand, the more logins that you have, the more accounts that you have to manage and clusters you have to remember their policies for, et cetera, et cetera. And how will you even get the accounts? Maybe you have some colleagues at these other universities, but do they necessarily have the power to help you get accounts? And maybe more importantly is that not all clusters use Condor. There are other job schedulers that institutions may use, Slurm, PBS, and Torque. And so for Condor, you guys are kind of taking a 2-week crash course to learn the interfaces, the command line, and the philosophy of Condor. And for these other job scheduling systems, those are all different. And particularly some of the philosophies may be different. So the way that the job scheduling behavior is for each of these job schedulers is going to be slightly different. And keeping all of that together in your head is going to be a difficult thing to do. But there is a really fundamental issue here with dividing jobs this way, because there's a difference between when you query the cluster and when you actually submit the jobs to the cluster. The state of the cluster and their idle resources may actually change between when you query and then when you do the actual submission. And because job scheduling can be kind of complicated, this may just be because there is a local user that has very high priority that submits jobs after after you query and then submit your jobs. So this method is inaccurate, and then it's also kind of tedious because you can imagine if you have 10 plus accounts into different clusters, you're going to be doing this a lot. So maybe we can at least deal with the tediousness of this. And we can call this automatic job division. And this is from The Simpsons, and from an episode where Homer changes his name to Max Power. And Homer says, "Kids, there's 3 ways to do things: the right way, the wrong way, and the Max Power way." Bart says, "Isn't that the wrong way?" Homer says, "Yeah, but it's faster." So the automatic job division may make the querying and job submission of clusters or for your jobs to these clusters a little faster, but there's still that fundamental problem of people locally or what have you may have higher priority and still just go before you. And so then your jobs are just sitting there. You also have to worry about developing and maintaining the system. There's an XKCD comic that talks about automating processes and what they look like in theory versus what they look like in reality. So when you're doing these repetitive tasks, you think, oh man, I'm tired of this. This is not a good use of brain power, so I'm going to write some code to solve this issue. And in theory, this will save you a bunch of time in the long run. But when you look at it, and especially in a complex system, you write the code, and then you have to debug the code, and then during debugging, you think, oh, maybe this could be, if I reorganize everything, then I can improve how this works, and then you spend more time working on your code base than doing your actual useful research. So if we want to have access to lots of other resources in a distributed high-throughput computing setup, there are some requirements that we should set before we decide on what the appropriate strategy is for this. First, you don't want to manage a lot of accounts, just 1 or 2, really a handful. You don't want to have to query and divide jobs because there are fundamental issues with that. You don't want to have to learn any other job schedulers, Condor only, please. And one thing that I didn't mention is that it would be, we really don't want to have to be forced to provide resources in this setup to be able to use other computing resources. So maybe you have a laptop or a desktop. You don't necessarily want to have to allow other people to use that when you're not using it to be able to enter into this distributed high-throughput computing setup. So this is where the OSG model comes in, and this is a bird's eye view of what it looks like. On the left here, you have you guys, the users, and you users have access to an OSG submit host, and there's a central manager that OSG submit host is connected to. There's some OSG infrastructure that lives in the internet, and then there is a remote cluster. There are many clusters in the OSG, but for purposes of this diagram, it's easier to just focus on the one. So as users, you have jobs, and then you submit them to the submit host, and this is what your jobs look like to me. And when the OSG notices enough jobs, and we call this job pressure, the OSG will submit jobs on your behalf to the cluster. And these are a special type of jobs. They're called pilot jobs. And these jobs will eventually start running, take up their equivalent of slots on the cluster. And before we get into what exactly these jobs are doing, I just want to remind you that in a Condor pool, we have a submit server, which you log into. And then you have the execute nodes. Then the execute nodes are split up into slots. And all of these nodes, including this submit node, report back to the central manager. And then the central manager does matchmaking based on your job requirements and what's available on the execute servers. And then the submit server and the execute server talk, and the submit server sends its jobs to the execute server. And once the job is done, it'll send results back to the submit server. So in the case of these pilot jobs, what they actually start up is this execute server software. And these execute servers report back to the central manager that is associated with your submit host, or your submit server. And these show up as available slots to you. And then with normal Condor mechanisms, your jobs will then start matching to these slots and running. So in this way, your jobs are kind of like the smallest doll in a Matryoshka doll setup. Your job is running within a pilot job that is running at the remote site or the remote cluster. So to recap, pilot jobs are special jobs. They are sent to clusters with idle resources when there's enough job pressure. The pilot payload is Condor execute server software, and the execute server reports back to the open science pool, where then your jobs can run within them. So in this way, pilots are leasing resources from clusters out in the OSG. These leases expire after a set amount of time, or if there isn't enough demand. And these leases can also be revoked by the cluster administrators. And this results in, on average, the open science pool having about 10,000 total cores. And when you start using the open science grid, you can very quickly ramp up to get at least 500 cores at a time, depending on your job requirements, but that's what we see on average. So does this meet our requirements list? We wanted minimal account management. You really only have to log into one submit server for access to the OSG. We don't want to have to divide our jobs between different clusters manually or even automatically. We just want, and this works because the pilot jobs show up as slots as if they're part of one big Condor pool. It's Condor only. The pilots report back as Condor slots, and you're going to be using a Condor submit server. And the OSG also doesn't require any contributions to actually use the OSG resources. You don't have to pay into the OSG, and approved researchers can use the OSG for free. And since you have all been accepted into the school, you're all approved researchers. So in actuality, the OSG model is a collection of many pools. Your jobs will run in the open science pool, and like I said, this is open to you. So it's focused mainly on individual researchers and campuses. The open science pool is one of many. There are separate pools for each virtual organization. And so here's a plot for how many compute hours that that various virtual organizations have used in the OSG over the years. And you can see that the very big juggernauts here are CMS and Atlas. And these are virtual organizations that are associated with CERN and the Large Hadron Collider. And these green bits are the OSG VO, or the Open Science Pool. So altogether, with the OSG model, we've contributed, or virtual organizations have used, I think at this point, over 10 billion hours or since about 2006. So that's pretty cool. Pilot jobs are awesome. But what's the catch? Distributed high-throughput computing requires a lot of complex machinery, but the OSG manages the hard bits, so you don't have to. Now, there are still some differences between an OSG setup, or using resources in the OSG pool versus your local high-throughput computing resources. One of these differences that will be most noticeable to you are the availability of resources. In the OSG, because there are resources from many different places, a lot of these resources are heterogeneous in terms of the software availability and the hardware availability. So here's a map of sites in the OSG, or clusters of the OSG. And you can see that most of them are concentrated in North America and in Central America. But we have sites that are all over the world. South Korea, it was actually pointed out that we don't have one in the middle of the ocean here. That is just that's supposed to be in the Netherlands. But you can imagine that at each of these clusters, they're managed by their own local administrators and facilitators, and they have their own policies and cultures, and sometimes with these international sites, they may not even speak the same language as you. So what does this result in? First off, there are the heterogeneous software resources. One thing you can depend on is that they're different. The operating systems of all of these servers are different variants of Linux, and they're all Red Hat based. There are varying software versions. There is some software provided by default. For example, you can expect at least Python 2.6. And then there's software availability. As like I've hinted at, a lot of the research-specific software that you may expect in a local high-throughput computing environment may not necessarily be available on the OSG execute servers. So, for example, you can't really count on BLAST being available. So how do you actually work around this? The solution is to make your jobs more portable in terms of software. You'll be learning more about that from Christina tomorrow in her talks and exercises. Additionally, the resources that are available in the OSG aren't quite as beefy necessarily as what you may expect in a local cluster. A lot of the resources that are made available to the open science pool are what, for example, CMS and Atlas, the LHC VOs, or the Large Hadron Collider VOs, are making available when they are not actively using their own resources. So most of the slots in the OSG, in the open science pool, are mostly single core. The RAM, each slot is mostly less than 8 gigs. There are some GPUs, but more are being added basically every day. And if you're used to a shared file system, especially if you're coming from an HPC background, that's not something you can necessarily depend on in the open science pool. So to deal with these resources that may not be as powerful standalone, but you have lots of them, you'll want to split up your workflow to make your jobs more high throughput. One difference in the OSG versus your local cluster is that you may have to be more cognizant of being a good user. You'll have to remember that you're running on resources that you don't own. Primary resource owners can kick you off for any reason. And this is very rare, but generally it happens if your job is using too many resources. You also don't have access to your local relationships. So your local systems administrators or your research facilitators, you can't petition them if you've been naughty and if your job or jobs have been using too many resources. Say, oh, I promise I won't do that again, and they'll sort things out. But in the case of the OSG, a lot of these resources are being donated, and if you're using too many resources, that may cause issues on the execute servers. And in a lot of cases, it'll take a lot of legwork for the local administrators to figure out exactly who you are, and then contact the right people to contact you to tell you to knock it off. So their first response will generally be to just kick your job off. You also have to realize, and this is kind of general for high throughput computing, is that you don't really want to put sensitive data onto or in your jobs, because these jobs are running on other servers. Other people have access to these servers. Other people being staff, sorry, may have access to these servers. So if there's data or software that you don't want to be shared, then that's something that you'll probably need your own private resources for. So it shouldn't be too hard to handle this this difference in policy. You just want to make sure to keep in mind that using shared resources is a privilege, and that you only want to use the resources that you request. In particular, you want to be nice to your submit servers. You guys have had access to Learn, and some of you may be starting to access the OSG submit server in the grid exercises. And you'll want to remember that a lot of your fellow researchers will be also using these submit servers. So if you're making the submit server slow, then you're going to be making it slow for everyone, and it's going to be a difficult bottleneck. So to counteract this, you're going to want to test jobs on local resources when they're available to you. You're going to want to test small and test often. And one tool to do this is Condor Submit with the -I or -interactive option. And basically, this allows you to submit a job, which once it starts up, you'll get a shell access or command line prompt, and be able to poke around the job environment to troubleshoot any issues you may be having with your job. And this is covered in tomorrow's exercises. A third difference that you may notice is that there may be slower ramp up. Leasing resources takes some time. Okay, so adding slots to the OSU, the Open Science Pool, takes some time with all the machinery that you saw with the job pressure and the pilot jobs and all that sort of stuff, versus in your local resources, the servers already exist and they're already connected to the central manager. So you don't really have to wait for the resources to magically appear. But the thing is, this doesn't really generally take a lot of time. It's on a scale of minutes. Compared to most job runtimes, which will last a couple of hours. And I think this is a small trade-off for increased availability. I'm sorry, one second. Is there a hand being raised or anything? Okay, never mind. But one tip that you should certainly consider is that if your jobs only run for less than 10 minutes each, you should consider combining them so that each of the jobs run for at least 30 minutes. Sorry, my cat is also, he wants attention now. Alrighty. So the reason that you want to do this is because the matchmaking cycle between jobs and servers generally will run every couple of minutes. And so if your job runtimes are similar in time to how long the matchmaking cycle is, then they'll be spending like close to half their time just waiting in queue. And if you can combine a series of these jobs, then your throughput will be better. Your jobs will be waiting in queue for the same amount of time, but the compute time will be spent, or the majority of your job's lifetime will be spent doing actual useful computing work. Good. All right. So in general, when using the OSG, like I said, you want to test small and test often. You want to specify your output error and log files at the very least while you're developing your workflow. In your own code, you'll want to store. You can implement something called self-checkpointing, and the idea behind this is that you'll store intermediate results. So if your job does get kicked off, then one thing that you can do in your own code is, periodically write out some results, and then in your code, when the job starts up next, you can have your code look at those intermediate results and start from there instead of the very beginning. You'll also want to add defensive troubleshooting in, say, your wrapper scripts around your actual code. And this is stuff to make sure you understand what, or that you have the proper environment or the expected environment. So you'll want to use ls-l to list the files that are in your current working directory where your job lands, to see that all the files are there as expected, and maybe checking to make sure that they're reasonable sizes or that they have the proper permissions on them. Also, PWD will tell you the path of your current working directory, which will tell you, will give you an idea of perhaps some errors in your code or what have you. Version and the name of the host that you land on, the hostname command, may also be very helpful if you need to contact the facilitation team to troubleshoot any sort of issues with a particular execute server you may be seeing. You can also add simple logging with print and echo statements, but you want to be strategic about this. You don't want to fill your disk with logs. So for example, if you have a for loop that has a couple hundred or 1,000 iterations, you don't want a print statement for each of those iterations. That probably won't provide you helpful information anyway. Right. Oh, there was a slide that was deleted. Good. All right, it was just a title slide though. Alrighty. So one thing that you also have to think about is security in the distributed high throughput computing model. And this, you have to remember that the internet is a scary place. The OSG staff does its best, but security is a game of risk mitigation and not perfection. And if anybody tells you that they have some product that is 100% secure and is perfect, then you should either A, run away screaming, or B, really think about what they're trying to sell you. We do use secure technologies to verify the identities of distributed servers. So kind of in the same way that if you go to gmail.com, your browser will tell you, oh, this is actually gmail.com. It will have like either a check mark or a shield or whatever, and you can take a look at their security credentials and that sort of thing. And we use the same underlying technologies. We also have a security team that tracks software vulnerabilities in response to security incidents. And not just any old cluster or user can join the OSG. So the virtual organizations verify and approve the users. So in this case, you guys will be part of the OSG VO with access to the open science pool. And through the interview process, we did our due diligence to verify that you have actual, research problems that you want to solve with more computing. The cluster owners themselves are responsible. They verify their own execute servers and their infrastructure at their local site. And then the OSG central staff verifies the clusters themselves. And most of the clusters that make up the OSG are academic institutions, like universities, or their national labs that have some vested interest in the research endeavor. But you're going to want to keep in mind that there are thousands of servers and users. So it's a lot to keep track of, and we try to mitigate security issues as best we can. But you want to keep in mind that no system can ever be perfect. Oh, here's the slide. It was just swap. Anywho, so what can you actually do for these security issues? Or what does this actually mean for you as a user? You're going to just want to keep in mind that you're using a shared computer that you don't own, so you're going to want to take basic precautions. It's like using any public computer at a library or what have you. Don't put your most private details on it and that sort of stuff. And you can take some basic precautions to protect your data. You don't want to have your files in a state that can be overwritten by other users. So if you're familiar with Unix style permissions, that means that you don't want your files to be world writable. I've mentioned it before, you don't want to put any private data or software on here. Certainly no HIPAA data, that would be very not legal. But anything that you don't necessarily want to be copied and you want to be able to look at these files, because even if they aren't maybe world readable or world writable, there may be some folks like staff that have administrator access to the servers. So for example, locally in the CHTC, our system administrators certainly have administrative privileges, but a lot of the CHTC staff, or all of the CHTC staff, also have privileges in case there are any issues. But that means that there are more people that may be able to look at top data. You also want to protect your account. Don't share your account with anybody. Pretty sure there are actually OSG policies for OSG Connect against that. And you'll want to use good passwords and password manager. And wherever possible, you'll want to use SSH keys.